This is my robot dog. I designed it myself and taught it how to walk. All seemed fine early on, but I discovered a slight issue. Every time it approached the ramp, it got stuck, unable to climb. I used reinforcement learning to fix this issue. Not once, but twice. And here are the outcomes. The first solution is subtle, but it takes a while to climb up. The second one is a lot faster, but I'm not sure how to put it. Perhaps it's a bit too fabulous, and maybe a little drunk. This is exactly what makes reinforcement learning powerful. With a little behind-the-stage crafting, you can allow your agent to discover solutions you would never imagine, or you can carefully guide it towards a narrow winning strategy. There aren't many YouTube channels that will teach you how to program a fabulous robot dog. So if you like this kind of content, consider subscribing to my channel before we get knee-deep into the video. In this tutorial, I'm going to show you how to implement reinforcement learning with two different strategies to obtain different solutions for the same problem. At its core, reinforcement learning is simple. An agent makes decisions and receives a score telling it how well it did. Over time, the agent gradually shifts its behavior toward whatever earns a higher score. In our first example, the robot gets total freedom to solve the ramp problem. In the second example, we restrict it to a single, well-chosen decision. Same robot, same ramp, same algorithm. Let's go over how and why each one comes up with their own unique solutions. If we give a policy complete freedom, it can discover creative solutions you would never think of. But the trade-off is a problem space that's huge, messy, and hard to stabilize. In this example, we give the network full control over the robot's movements. Like a user with a gamepad controller, it's allowed to change the robot's height, speed toward a direction, pitch its nose up or down, and blend between normal walking mode and a dirt mode, which utilizes higher walking steps. In order to gather experience quickly, we spin up 14 separate simulation processes with 12 robots each. That's 168 robots gathering experience every control step. More diverse, less repetitive data means steadier learning and a policy that generalizes instead of memorizing one lucky run. The network never lets go of the stick. It has to keep walking, steering, balancing on the incline, and timing its tilt, as one continuous stream of commands. This is the figure it out however you want version, and its reward function has to do a lot of work to keep that much freedom from going sideways. The reward function is the most important part of reinforcement learning. The robot doesn't know what a ramp is, and it doesn't know falling is bad. All it has is a score every step, and its whole objective is to make that score bigger. If you get the reward shaping wrong, the robot will happily find a cheap and tricky way to earn points without doing what you actually wanted. The only way to prevent that is to carefully shape the reward function to steer its behavior toward the outcome you actually want. Instead of walking through all 14 reward function terms, it's easier to think of them in 4 buckets. The first bucket is about staying alive, a small bonus just for standing still, and a heavy penalty for falling. The second bucket is about making real progress. Reward for forward speed, a milestone bonus that only pays out on a brand new farthest point ever reached, and a big one-time bonus for actually getting on the ramp. The third bucket is about staying balanced and online. There are penalties on the body height error, roll, yaw, sideways drift, and how fast it's rocking or wobbling. The fourth and the last bucket is about staying smooth. Penalties on how large its actions are, how much they change frame to frame, and how fast its joints are moving and accelerating. With this much continuous authority, the policy will happily find a jittery or twitchy way to satisfy everything else, unless you explicitly punish the twitchiness. That's a lot of reward function terms, and that's the point. Total authority over the whole day needs a lot of guardrail, or it will find a way to cheat its way to a high score and will never achieve what you want it to do. While the training runs in the background, we need a way to observe the learning progress. For that, we will use TensorBoard, a live dashboard that shows the progress of your each training indicator on your browser. Why bother? Because a single reward number on your terminal log doesn't tell you much. Through TensorBoard, we observe the overall trends so you can see if the agent is actually improving. It's the easiest way to tell whether the training is really learning or just spinning its wheels. For this example, you want to watch mount success rate steadily rise. But because there are so many competing terms here, it's worth scanning the other components too. If the success rate is rising, while penalty terms like row stay flat instead of shrinking, that's a sign it found a way to walk forward while ignoring balance. I know, you can already guess the outcome of this example from earlier in the video. So how about we skip the review and move on to the next example. In this example, we restrict our policy to a single well-chosen decision, so it learns fast and stays predictable. But it's strictly limited by whatever boundary we set. This one also works on a different foundation than our first example. Instead of the hand-coded inverse kinematics controller, it's built on top of a base neural network. Therefore, the new neural network we are about to train will work alongside an old one. The new network doesn't control the robot step by step. Instead, when it detects the robot is stuck near a ramp, it engages once and lets the base controller regain momentum. Once every foot has touched the ramp, it disengages completely and the base neural network just walks normally again. Because the action space here is so much smaller, the reward function has fewer elements too. We still have some of the same terms, like the progress and milestone bonuses. But there's nothing to smooth out. Because this policy makes exactly one decision per attempt, there is no frame-to-frame jitter to punish. For this example, the reward function is designed to answer one focused question well. Given exactly how the robot is stuck, what is the best configuration to get it unstuck and onto the ramp? And what do we do once the training is over? Well, we don't just trust the training scores and decide it succeeded or not. Instead, we load the saved model and run it deterministically on fresh episodes it's never seen. At this point, you can watch a single robot in windowed mode to see how it moves. Or you can run it in headless mode across dozens of robots for a more analytical evaluation. And now, finally, let's look at our trained models together and judge their performance. The good news is, both models achieved high success rates in training, and through observation, we can clearly see that they can climb onto the ramp. So our reward functions worked well. And as expected, their behaviors are completely different. Notice how the second example didn't change the base net's walking style at all, which is exactly what we wanted and what we expected. The first example, on the other hand, figured out if it keeps moving its legs sideways while it's walking up the ramp, it avoids getting stuck. That's exactly the kind of behavioral difference that can emerge from the same objective when you change how much freedom the agent is given. On the contrary to the general misconceptions about it, reinforcement learning is not a hands-free method. It takes a lot of practice and careful crafting to obtain useful solutions. Through different training configurations, reinforcement learning can discover unique properties. And if you want to experiment with it yourself using the examples from this video, you can find the links to my GitHub repo down in the description. Thanks for watching, and if you liked the tutorial, consider subscribing to the channel.